Hello, everyone. I'm sorry that I haven't posted anything in a while. I've been struggling a little bit, just trying to get everything on here and figuring out, how all of this is going to work. So I apologize for that. But um, this is still just continuing with integration. We're going to do integration for the rest of the year. So you'll see this is on definite integration. But first, I just wanted to give you a little bit of background on why we do integrals. So derivatives is what we've been doing all year long. And we know, hopefully you know by now, that a derivative is the slope of the tangent line. Remember, we always say derivative is slope, derivative is slope. That's always what we're talking about. And if you remember way back at the beginning of the year, we looked at if I have a graph, something like this, and I want to know the slope of this point right here, the instantaneous slope. If you remember, what we did was we looked at 2 points and we found the slope of that line that connected them. And then we wanted this point to move closer and closer to that one. And we were looking at the limit of that distance. So we were looking at the limit of this distance as it went to 0. So we wanted this to keep getting smaller and smaller and smaller and smaller until it was eventually 0. That was how we found the derivatives. If you remember way, way, way back in September, we did all of those limits and it took a really long time until we learned all of the shortcuts. Well, now we're kind of going to do the same thing, but with integrals. So what is an integral? What should you be thinking about when you see this symbol right here? This. What should you be thinking? Just like we've said all year, derivative means slope, derivative means slope. Well, what does the integral mean? Okay, well, if we think about a graph, and again, it's a little bit difficult to draw on this screen, so I'm trying my best. Okay, think about this graph, and let's say I have this is my curve. Let's say that's f of x. Well, if I wanted to find the area under the curve, so what that means is, let's say I have a value here of a and a value here of b. Let's say I want to find this area. So the area above the x-axis between these two vertical lines, A and B, and then the top here is curved. Now, if it was straight across, it would be easy because it would just be a rectangle, but it's not, it's curved. So the way we would figure this out is, I'm going to break this up into little rectangles. So let's say I break it up here, and then again here, and then again here. And I'm trying my best to fit it with rectangles, but you see, it's not exactly going to fit. But if I could make these rectangles skinnier and skinnier and skinnier and have more of them, then that would give me a very close approximation to what the area under this curve would be. Now, I'm going to write all of these symbols that you probably won't understand what that means, but what this is actually doing is, if I want to take the area of these, I'm going to take the sum of all of those areas, and that big E, that big sigma just means sum, and this is the area of the rectangle. So f of xi would be the height of the rectangle, and xi would be the width of the rectangle. So this is length times width. It's just giving me the area of that rectangle. If I would find the limit of adding up all of those rectangles, and not x, it should be n. And n is just the number of rectangles. So if I say there's an infinite number of rectangles in here, and I'm going to add up all the areas of those rectangles, that would equal my integral. That's what an integral does. An integral finds the area under the curve. So when you think of integrals, that's what you should be thinking of, area under the curve. So that brings us to the fundamental theorem of calculus, pretty much the most important thing that calculus deals with, okay? If a function is continuous over an interval, and capital F is the antiderivative, which we already found how to do, it's just going backwards from taking the derivative, then this is true. So notice now that there's numbers here on my integral. Before, we just did indefinite integrals. That's why we added that plus c. Like I said, there's numbers here now. Before, we just did indefinite integral. Sorry about that. I was having some technical difficulties there. So I believe I was talking about the difference between indefinite and definite integrals. We have numbers here now instead of just adding plus c because we weren't sure where this was taking place. So that extra constant could have been anything. But now you'll see we don't have that plus c anywhere. And that's because they would subtract away if we did have them. So now we're going to get definite answers. We know we want the area under the curve from here to here. So you're not going to need the plus c when you're finding a definite integral. So my first example, and you'll see the integral is still here. Now when I write the integral on this program, these numbers are really close together, but when you see them in the book, you'll see that they're drawn a little bit more like this, 1 to 2, x squared minus 3 dx. It's just my program here puts the integral really close together. But so this is saying, what this is asking is if I were to graph this, so x squared minus 3, so that's going to look something like this. What it's asking for is from 1 to 2, what's this area here? Okay, so we're going to find that. So the first thing you want to do is take the antiderivative just like we had before. So I'm going to add 1 to my exponent, making it 3, then divide by that 3. So I'll have 1/3 x cubed minus 3x. Now, normally we would add the plus c, but we're not going to do that. Instead, we're going to take this from 1 to 2. So now, what the fundamental theorem of calculus tells us is I'm going to plug in 2 for x, and I'm going to plug in 1 for x. And I'm going to subtract those. So I'm going to put parentheses around them so we remember what's what. So now I'm going to run out of room here, so I'm going to try to do some of this without writing every single step. So this is going to become 8/3 minus 6 minus, this will become 1/3 minus 3. Okay, so that gives me 8/3 minus 1/3 is 7/3. And then -6 plus 3 is -3. So 7/3 minus 3 is -2/3. So that's going to be our answer. There's no plus c. Okay, that's going to be our actual area under that curve. It's 2/3. So for the next one, okay, first thing I'm going to do is rewrite it because I want this to be an exponent. So this is really the integral from 1 to 4 of 3 to the x to the 1/2 dx. So first thing I'm going to do is take the antiderivative. So I'd add 1 to my exponent. That would make it 3/2. And then I'm going to divide by that fraction, which remember is like multiplying by the reciprocal. So this is going to give me 2x to the 3/2. And again, we're not adding plus c. We're going to take this from 1 to 4. So that's going to be, I'll plug in 4 and subtract, plugging in 1. So 4 to the 3 halves is 8. So 2 times 8 is 16. Minus 2, that area would be 14. So for all of these problems, you're going to get definite numbers. You shouldn't have any x's left because we're finding an area, and you shouldn't have any plus c's or anything like that. Everybody should be getting the same exact answers. Now, there will be just a few trig ones in there for us to do. And you can see that now it's 0 to pi, because if you remember our graph, when we graphed these, it was a lot easier to break our x-axis down by radians instead of by x values. But still, we're going to go through this process the same way. So taking the antiderivative of 1, that's just going to become x. And then the antiderivative of sine is going to be negative cosine. And again, no plus c this time. Now we're taking it from 0 to pi. So I'll plug in pi for x, and I'll plug in 0 for x. And remember, we're going to subtract those. So pi minus, the cosine of pi is negative 1, minus 0, plus, because don't forget to distribute your negative, cosine of 0 is 1. So now I have pi plus 1, which gives me pi plus 2. And pi is just a number. It's just 3.14. So that's fine to have that in your answer. And so my answer there is just pi plus 2. Now, if you wanted to try these last two on your own, you could. So if you want to pause the video, try them on your own, see how you do, and then you can come back and replay it to see if you got the right answers. You can go ahead and do that. So first I take my antiderivative. It's going to be from 1 to 3. So then I'm going to plug all this in. And I'm going to subtract, plugging in 1. Okay, so I get 27 plus 45 over 2 minus 12. Now when you go to do the second quantity here, don't forget to distribute your negative. So I have minus 1 minus 5 halves plus 4. And then when you add all those up, combine all those together, you get 38. And now for the last one. So there's no x here. So when I take the antiderivative, it's just going to become 2x from 7 to 2. So that'll be 2 times 7 minus 2 times 2. So we end on a nice, easy one here. So 14 minus 4 is 10. Okay, so it's really just taking the antiderivative like we did before, but now instead of adding c, you're going to actually find your answer. Your homework here is at the bottom. Now, just so you know, the book sometimes changes the variables. You'll see t's and u's and s's. You can change everything to x if you want, just to make it simpler. But when I did the homework, I did use the variables that they did. But it's all the same process. Nothing changes. So if you want to change those to x, you can. This whole thing is worked out on the classroom. If you have any questions, please don't hesitate to ask. This homework is not one that is assigned